So as usual in this worded question, I would start by writing out the sequence that is generated by this context. In writing it out, it becomes clear that it is a geometric progression with a common ratio of 1.05, and the first term A is 100. So in part A, when we're looking for the amount of money in the account after 9 months, we need to add all these terms up. So a geometric series, we're adding them up with the sum to 9 is what I'm looking for. So first of all, I'm going to write down the sum to n. Write down your formula. I always use this formula just because that's the one that's in my head, that's the one that I remember. Probably with r greater than 1 here, you might want to use the other version where these are switched over. They give the same answer either way. So plugging in our values for a and r, and n being 9, plug it straight in the calculator, and there's our answer, correct to the nearest pence. So we now want to find n, the first month where there is more than £6,000 in the account. So again, we're looking at this sum to n, and we need to show this expression involving the logs, or this inequality. Do not start with what we are trying to show. Kind of ignore that bit for now. The first month in which there is more than £6,000 in the account, so I'm looking for my value of n that gives me the sum to n is greater than 6,000. Plug in the formula. I have taken care to use this version of the formula this time because I'll have 1.05 minus 1 on the bottom, so this just avoids the negatives when r is greater than 1. So plug in our values for a and r. The denominator here is 0.05, so I'm going to multiply up by that. Divide both sides by 100, and then add 1. If I look at where I'm trying to get to, this is looking promising. I've got 1.05 and I've got 4, and my unknown n is in the power. So I need to take logs of both sides, and then I can bring that n down using my log laws. It doesn't matter which base log I use as long as they're the same. The assumption here is that this would be log to the base 10. I could equally have written n ln 1.05 is greater than ln 4. That would just be log to the base e. Now, one final consideration here, as you are dividing by a log of 1.05, you want to check that that is positive. Just refer you back to our diagram of the log curve. Remember, it looks like this, where log of 1 is 0, and anything between 0 and 1 would be a negative value for log, and above 1 would be a positive value. So I can just sort of consider that and think, yes, log of 1.05 is positive, so I can then divide by that and keep the inequality sign the same way around, log of 1.05, and that is what they've asked me to show. Okay. So in part C, again, I would start by writing out the sequence generated by this worded context. And I can see that actually now we're in a different situation. We have an arithmetic progression. So we're looking at our first term, A is 50. Our common difference, D, we don't know. And we've got N, we want it to be 29. And we want a total of 6,000. So we want our sum to n to equal 6,000. So just by writing those down, and then I can plug it into my formula for the sum to n. So write down the formula first. Sum to n equals n over 2 times 2a plus n minus 1d. Plug in everything we know. My first marks are just for plugging in these numbers into the formula, so I wouldn't worry too much about evaluating much at the moment, but I'm going to multiply up by 2 there. We have 100 plus 28d equals 12,000, and continue to solve it for that. And I get £11.21 for 2 marks.